Hi everyone, I'm Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This is lecture 8. Response spectrum of seismic record. Seismic record is a record taken during an earthquake. Response is structural responses, including displacement, velocity, and acceleration. Spectrum is something to do with frequency or period. Therefore, in this course, in this lecture, we are going to talk about the maximum responses of the structure with different vibration period under the same seismic record. And here are some terminology. Seismic record is the record taken during an earthquake. Response spectrum is the relationship of maximum structural responses with structural vibration period. And in Chinese, 反应谱. Seismic record in Chinese, 地震记录. There are three kinds of response spectra. One is a displacement response spectrum. Is the relationship between peak relative displacement of the structure with the structural vibration period. In Chinese, 位移反应谱. Velocity response spectrum is the relationship between peak relative velocity of the structure with the structural vibration period. And in Chinese, 速度反应谱. Acceleration response spectrum is the relationship between peak absolute acceleration of the structure with its vibration period. In Chinese, 加速度反应谱. Spectral displacement. Given the structural vibration period, then we can have the maximum structural relative displacement. And in Chinese, 谱位移. Spectral velocity. Given the vibration period of the structure, then we can have the peak relative velocity of the structure. And in Chinese, 谱速度. Spectral acceleration. Given the vibration period of the structure, then we can have the peak absolute acceleration of the structure. And in Chinese, 谱加速度. And here is the motion equation of the structure. And then this one is the initial conditions of the structure. And this is the motion equation under base excitation. And the base excitation is described in the form of ground acceleration. And according to the previous lecture, we can have the first order difference equation for structural relative displacement from the information at current step n, including displacement, relative displacement, velocity, relative velocity, and ground acceleration. Then we can calculate the relative displacement at next step. And if we repeat the process step by step, then we can obtain the relative displacement at all steps. And A11, A12, and B1 bar are coefficients determined by the natural frequency of the structure, omega 0, damping ratio of the structure, zeta, and sampling period of the external vibration, delta t. Therefore, A11, A12, B1 bar are all constants. They do not vary with time. Similarly, we can obtain the first order difference equation for relative velocity with the information at current step n, including relative displacement, relative velocity, and ground acceleration. We can calculate the relative velocity at next step n plus 1. Similarly, if we follow the step, repeat the step one by one, then we can obtain the relative velocity of the structure at all steps. A21, A22, and B2 bar are coefficients determined by the natural frequency of the structure, omega 0, damping ratio of the structure, zeta, sampling period of excitation force, of the ground acceleration delta t. Therefore, A21, A22, B2 bar are coefficients that do not vary with time. They are constants. And from the equilibrium equation, we can obtain the absolute acceleration with the information of the relative displacement x and relative velocity x star. We can compare the absolute acceleration of the structure. With these three equations, we can solve the relative displacement, relative velocity, and absolute acceleration. Therefore, given a seismic record, we can have x0 double dot, and it is recorded every delta t, so that we can have the information about the ground acceleration at 0 delta t, 1 delta t, 2 delta t, and so forth. Since A11, A12, B21 bar, A21, A22, B2 bar can be determined by the natural frequency of the structure omega 0, damping ratio of the structure zeta, and sampling period delta t. Because the seismic record is given, therefore the ground acceleration is given, so that delta t is fixed. And then, therefore the structural responses of the structure, including the displacement, velocity, and acceleration, they vary with the natural frequency and damping ratio of the structure. Therefore, relative displacement x, relative velocity x star, and relative acceleration are functions of omega 0, zeta, and zeta. From all steps of the displacement, we can find the maximum displacement. That's the peak relative displacement, x maximum. Similarly, we can have the peak relative velocity, x dot maximum, and also the peak absolute acceleration, x double dot a maximum. Therefore, x maximum, x dot maximum, and x a double dot maximum are all functions of omega 0 and zeta. Therefore, the peak structural responses, including the peak relative displacement, peak relative velocity, and peak absolute acceleration, are functions of omega 0 and zeta, given the seismic record, the ground acceleration. Since structures, civil engineering structures are largely damped, so that we can assign the damping ratio to be 0.05, that is 5%. Therefore, the peak displacement, the peak relative displacement can be reduced to be a function of omega 0, or the function of the vibration period t. Therefore, x maximum is a function of t, the vibration period of the structure, so that we can have the displacement response spectrum. This is the relationship between peak relative displacement with structural vibration period t. Similarly, when we assign the damping ratio to be fixed to 5%, so that the peak relative velocity can be reduced to a function of omega 0 or a function of vibration period t. Therefore, we can obtain the velocity response spectrum. It's the relationship between peak relative velocity of the structure with the vibration period of the structure. Finally, we can have the acceleration response spectrum. Since the damping ratio zeta is fixed to be 5%, so the xa double dot can be reduced to a function of omega 0 for a function of vibration period t. Therefore, we can have the relationship between peak acceleration, peak absolute acceleration of the structure with vibration period t, and it is called acceleration response spectrum or absolute acceleration response spectrum. Therefore, response spectrum is the relationship between peak response, including peak relative displacement, peak relative velocity, or peak absolute acceleration. and the natural frequency or the natural period of single degree of freedom structure under the same base excitation. Therefore, given the ground acceleration, we are going to find out the peak responses, including peak relative displacement, peak relative velocity, and peak absolute acceleration. Therefore, from this graph, you can know that the horizontal axis is the vibration period of the structure. The vertical axis is the peak responses. It may be displacement, velocity, or absolute acceleration. And take absolute acceleration as an example. The horizontal axis is the structural vibration period. It changes from 0 to 5 seconds. And the vertical axis is the spectral acceleration in Gauss. And the damping ratio of the structure is fixed to 5%, so that the peak absolute acceleration is a function of structural vibration period. Okay, under the same excitation, the same ground acceleration, the peak structural responses vary with a structural vibration period. And here's an example. And this is a seismic record taken in the station TCU 026. And this is the ground acceleration. The horizontal axis is time. The vertical axis is the ground acceleration. And the unit is centimeter per second square. And this is the equation motion of the structure under base excitation. And x double dot plus 2 zeta omega 0 x dot plus omega 0 square x equal to minus x0 double dot t. Therefore, the response of the structure, given the ground acceleration, the response of the structure is function of omega 0, the natural frequency of the structure, zeta, the damping ratio of the structure. And this is the ground acceleration, and is used to drive the structure. And then after the seismic analysis of the structure, we can have the time history of the relative displacement. And given the natural frequency of the structure to be 6.28 radian per second, and the natural period of the structure equal to 1 second, and the damping ratio is fixed to 0.05. And after seismic analysis, we can have the time history of the relative displacement of the structure. And from the time history of the relative displacement of the structure, we can have the maximum value of the peak responses. And it is found that it is 3.45 centimeter. Now we change the vibration period from 1 second to 2.5 seconds, so that the natural frequency becomes 2.51 radian per second. And the damping ratio of the structure is still fixed to 0.05. And after seismic analysis of the structure, we use this ground acceleration to drive the structure. And omega 0 is 2.51 radian per second, and the damping ratio is 0.05, so that we can have the time history of the relative displacement. Once we have the time history of the relative displacement, then we can pick up the peak one, and it is found to be 13.54 centimeter. Okay, when t, the natural period of the structure equal to 1 second, the peak relative displacement equal to 3.45 centimeter. When t equal to 2.5 seconds, the peak relative displacement is found to be 13.54 centimeter. And if the natural period of the structure is changed to be 0.5 seconds, and the peak relative displacement is found to be 142 centimeter. And if the natural period of the structure t is assigned to be 4.0 seconds, and after seismic analysis, we found that the peak relative displacement to be 21.70 centimeter. If we have more data points, and we can connect all the data points, and then we have the curve. This is the relationship between peak relative displacement and structural period, and it is called displacement spectrum or relative displacement spectrum. Similarly, for velocity, when t equal to 0.5 seconds, we can conduct the seismic analysis, and from the velocity, the relative velocity of the structure, we can find the peak relative velocity to be 15.59 centimeters per second. And when t equal to 1 second, conduct the seismic analysis, find out the time history for the relative velocity of the structure, and pick up the peak value, and it is found out to be 22.77 centimeters per second. When t equal to 2.5 seconds, conduct the seismic analysis, and then find out the peak relative velocity to be 32.34 centimeters per second. When t equal to 4 seconds, and the peak relative velocity is found to be 40.11 centimeters per second. We can have more vibration period, and then connect all the data point. Then we can have the curve, and the curve shows the relationship between peak relative velocity and structural vibration period t, and it is called velocity spectrum. Similar for acceleration, when t equal to 0.5 seconds, conduct the seismic analysis, find out the peak absolute acceleration, and then we got a data point. When t equal to 1 second, conduct the seismic analysis, then we can have the time history of the absolute acceleration of the structure, and pick up the peak value, so that we can have 1 point here. When t equal to 2.5 seconds, conduct the seismic analysis to obtain the time history of the absolute acceleration of the structure, and pick up the peak value, and then we can have another data point here. When t equal to 4 seconds, conduct the seismic analysis, find out the peak value, and then we can have one more point here. If we can have so many data points for different vibration period, then we can connect all the data points in order to have a curve, and it's the relationship between peak absolute acceleration and structural vibration period t, and it is called acceleration spectrum. And here is displacement spectrum, and this is the plot of acceleration spectrum. When t equal to 0, and when t tends to 0, and t is the vibration period of the structure. When t is very, very small, that means that the structure is so rigid, so that the structure moves with the ground. Since the structure moves with the ground, therefore there's no deformation in the structure. The relative displacement of the structure equal to 0, therefore the peak relative displacement of the structure equal to 0. And since the structure moves with the ground, the acceleration of the structure equal to the ground acceleration. Therefore, the peak absolute acceleration of the structure equal to the peak ground acceleration, PGA. Therefore, when t tends to 0, x maximum, the peak relative displacement equal to 0, and the peak absolute acceleration of the structure equal to the PGA of the ground acceleration. When t tends to infinity, therefore the natural period of the structure is so long, the structure is disconnected from the ground. Therefore, there will be no absolute displacement. If you observe from the outer space, there will be no absolute displacement of the structure. Therefore, the relative displacement equal to the peak ground displacement, x maximum equal to peak ground displacement. Since the structure does not move when you observe from the outer space, therefore the absolute acceleration of the structure equal to 0. In short, when t tends to infinity, x maximum, the peak relative displacement of the structure equal to the peak ground displacement, and the peak absolute acceleration of the structure equal to 0. Therefore, when t tends to 0, there will be no displacement, no relative displacement. When t tends to 0, the absolute acceleration, the peak absolute acceleration of the structure equal to the peak ground acceleration. When t tends to infinity, the displacement of the structure equal to the displacement of the ground. Therefore, the peak displacement of the structure, peak relative displacement of the structure, equal to the peak ground displacement. When t tends to infinity, the structure does not move when observing from the outer space. Therefore, there will be no absolute acceleration. Therefore, the peak absolute acceleration of the structure equal to 0. And we take 5%. We have already assigned the damping ratio of the structure equal to 5%. Therefore, we use the damping factor, damping ratio 5% as a reference. When the damping ratio is smaller than 5%, then we can have the blue line here. The response of the structure becomes higher. And this is for 10%, 20%, 30%, 40%, and 50%. And you can observe from all these curves that when the damping ratio becomes higher, the response of the structure becomes lower. And this is the displacement spectrum. And this is for velocity spectrum. And we take damping ratio equal to 5% as a reference. When the damping ratio is less than 5%, the velocity response, the peak velocity, the peak relative velocity of the structure becomes higher. When the damping ratio is higher than 5%, the peak relative velocity of the structure becomes lower. And this is 2%, 5%, 10%, 20%, 30%, 40%, and 50% for the damping ratio of the structure. When the damping ratio becomes higher, the peak velocity of the structure becomes lower. Therefore, the velocity spectrum is lower when the damping ratio becomes higher. And this is for acceleration spectrum. We also take 5% as a reference. When the damping ratio is less than 5%, the acceleration spectrum is higher. When damping ratio is higher than 5%, the acceleration spectrum becomes lower. And this is 2%, 5%, 10%, 20%, etc. Therefore, the higher the damping ratio, the lower the displacement spectrum, the lower the velocity spectrum, the lower the acceleration spectrum. And here we have acceleration spectrum for different records. This is the record from the station TCU 026, the record from station TCU 029, the record from 6Y008, the record from El Centro. And this is the acceleration spectrum. And the horizontal axis is the structural vibration period of the structure. And the vertical axis is the peak absolute acceleration of the structure. If the vibration period is larger than one second, and you can observe that when the damping period becomes higher, the acceleration spectrum becomes lower. And if you observe the vibration period in the range from 0 second to maybe 0.2 second, and you can observe that the acceleration spectrum becomes higher when the vibration period becomes higher. So that you can have, even for different seismic record, you can have similar pattern. When the vibration period is small, the acceleration spectrum increases. And then you reach peak values between maybe 0.2 second to 0.8 second. And after that, the acceleration spectrum decreases with the increase of vibration period t. Therefore, even for record from different stations, we have a similar acceleration spectrum. Response spectrum is a curve of maximum structural response, including displacement, velocity, and acceleration versus vibration period T. And here is the model of a single degree of freedom, and it can be modeled by mass, spring, and damping system. And under ground acceleration, x0 double dot, then we can have the structural responses, and here is displacement response. And displacement response spectrum is a curve of maximum structural relative displacement versus a structural period. Therefore, displacement response spectrum is the relationship between peak structural relative displacement and structural vibration period. Velocity response spectrum is the maximum relative velocity versus structural vibration period. Therefore, velocity response spectrum is the relationship between peak structural relative velocity with structural vibration period. Acceleration response spectrum is the maximum absolute acceleration of the structure versus structural vibration period. Therefore, acceleration response spectrum is the relationship between absolute acceleration of the structure versus period of the structure. And here is the maximum structural relative displacement. It is a function of vibration period T and damping ratio zeta. After seismic analysis, we can have the relative displacement at all steps. Then from all steps, we take the absolute value and then find out the maximum one. And this is the peak relative displacement of the structure. If we assign the damping ratio to be 5% or 0.05, as SD, the relative displacement spectrum becomes a function, can be reduced to be a function of vibration period T. Once we assign the vibration period T, then we can have F0. F0 equal to the reciprocal of the vibration period. From 0, we can have omega 0. Omega 0 equal to 2 pi F0. Once we have the omega 0, the natural frequency of the structure, the damping ratio of the structure, we can conduct the seismic analysis of the structure. After conducting the seismic analysis of the structure, we can have the relative displacement at all steps. Then from all these steps, we can have the peak relative displacement. Then this is SD. Once we have the peak relative displacement for all vibration period T, then we can have the relationship between peak relative displacement and structural vibration period T. Similar for relative velocity. Originally, the peak relative velocity of the structure is a function of T, the vibration period of the structure, and zeta, the damping ratio of the structure. Now we fix the damping ratio to be 5%. Therefore, the peak structural relative velocity is reduced to be a function of vibration period T. Once we assign the period, we can have the frequency F0 and the omega 0. Omega 0 equal to 2 pi F0. From omega 0 and zeta, we can conduct the seismic analysis of the structure so that we can have the relative velocity of the structure at all steps. From this information, we take the absolute value and find out the maximum. There's the SV, that's the peak relative velocity of the structure. Once we find out the peak relative velocity of the structure for all the vibration period, then we can plot the curve between SV, the peak relative velocity of the structure, and vibration period T. and this is the velocity response spectrum of the structure. Similarly, for structural absolute acceleration, given the ground acceleration, x0 double dot, and we fix the damping ratio to be 5%, 0.05, therefore the peak absolute acceleration is reduced to be a function of structural vibration period t only. When we assign the structural vibration period, then we can have f0. f0 equal to 1 divided by t. From f0 we can have omega 0, and omega 0 equal to 2 pi f0. Once we have the natural frequency of the structure omega 0 and the damping ratio of the structure zeta, and the ground acceleration is given, we can conduct the seismic analysis of the structure. And after conducting the seismic analysis of the structure, we can have the absolute acceleration of the structure at all steps. And this is the relative acceleration with respect to the ground, and this is the ground acceleration. When we add these two up together, we can have the absolute acceleration. Once we have the absolute acceleration at all steps, then we can take the absolute value and find out the maximum one. Then we can have the maximum structural absolute acceleration, and it is a function of t. And here's an example, and this is a seismic record taken in the station TAPO 97, and the east-west direction, because there are three components for the record, and we take out the east-west component for consideration. And the earthquake event is Hualien earthquake, occurred on March 31st, 2002. And the sampling period for the record, delta t, equal to 0.004 seconds. And the time length of the record is 99.996 seconds. Therefore, the number of data points n equal to 25,000. And the peak ground acceleration, PGA, equal to 96.24 Gale. And 1 Gale equal to 1 centimeter per second square. And this is the seismic record. The horizontal axis is 10. The unit is second. The vertical axis is acceleration. The unit is scale. And the peak ground acceleration occur here is 96.24 Gale. And the sampling period, delta t, equal to 0.004 seconds. And this is record taken from the station TAPO 97. And the component, east-west component, is taken into consideration. The damping ratio here is fixed to be 5%, there's a 0.05, and the structural vibration period varies from 0.01 second to 0.1 second to 1.0 second, and then to 10 seconds. Therefore, we can have the range of the vibration period from 0.01 second to 10 seconds. And this is the ground motion. The initial condition are assigned to be 0. After conducting seismic analysis, we can have the peak relative spectrum for different vibration period, the peak relative velocity for different vibration period, and also the peak absolute acceleration for different vibration period. If we connect all the data points, then we can have the displacement spectrum, velocity spectrum, and acceleration spectrum. And this is the video for lecture 1. This is the video for lecture 2 in Chinese and English version, video for lecture 3, and video for lecture 4, and videos for lecture 5, and videos for lecture 6 and lecture 7, and video for lecture 8. And here is the website for the Chinese version, and English version one is under construction. This is the current one. Okay, from this lecture, we talk about the response spectrum of seismic record. Given the seismic record, we can have the ground acceleration, and also we can have the sampling period of the ground acceleration. And also the damping ratio is fixed to 5%. Then we can conduct the seismic analysis of the structure. After conducting the seismic analysis of the structure, we can have the peak responses, and they vary with the vibration period. So that we can have the displacement spectrum is the relationship between peak relative displacement of the structure with vibration period of the structure. Then we can have velocity spectrum is the relationship between peak relative velocity of the structure and structural vibration period. We can also have the acceleration spectrum, and is the relationship between absolute acceleration of the structure with structural vibration period. Once you know the vibration period of the structure, then you can look up from the displacement spectrum to find out the maximum relative displacement, from the velocity spectrum to find out the maximum relative velocity of the structure, and from the acceleration spectrum you can find out the peak absolute acceleration of the structure once the vibration period of the structure is given. That's all for this lecture. Thank you. See you again. Bye bye.